Interstellar.
What is a dimension? Is the world two-dimensional? In theoretical physics, the universe is thought to contain many dimensions. So where exactly are those dimensions? It is said that the quantum world has extra dimensions. Extra dimensions are dimensions beyond the three we perceive: length, width, and height. If you look into the universe, you can discover new dimensional realms, such as the black hole holographic principle. After hearing today's talk, you will understand dimensions, and your view of the world will change. I will show you a world full of surprises, just like science fiction. What is a dimension? A dictionary says it is the degree to which space extends in mathematics. It is expressed by the number of coordinates. A line is 1D, a plane 2D, and a solid 3D. It also means a standpoint or level when thinking or acting. That talk is low level, or these are problems on different levels. Euclid, called the father of geometry in ancient Greece, defined a point as something without parts, a line as length without breadth, a surface as having only length and breadth, and a solid as having length, breadth, and height. He set these definitions. We still learn these definitions today. It is amazing they were conceived before the Common Era. Later, the philosopher Descartes created the concept of dimensions and visualized it. 0 dimensions are a point, 1 dimension a line, 2 a plane, and 3 a solid. He expressed them by coordinate counts, marking scales to draw figures. Descartes also invented the number line, thus generalizing negative numbers. Compared with a mere line in 1 dimension, 2 dimensions are far more complex and can show many shapes. 3 dimensions are even more complex. The world we live in is surely 3-dimensional. Put simply, it has 3 axes: length, width, and height. No one has ever created a 4-dimensional object in this physical world. Even so, we can use 4 or more dimensions as tools. For example, computers routinely handle multiple dimensions. Computer processing happens in software, a virtual world. Therefore, it is not bound by 3D constraints. In a spreadsheet, treating each column as one block is a 1-dimensional array. You can add another array inside each cell of that array. This state is called a 2-dimensional array. It corresponds to the table we often use. You can of course nest arrays inside the inner array again. That is like stacking sheets of paper filled with tables. In a spreadsheet program, it becomes the total of all sheets. Because the screen is 2-dimensional, what you can grasp at once is the 2D table. In physical reality, stacking such sheets makes a 3D object, but you cannot grasp all its content simultaneously. Still, you can recognize or express that it exists. Likewise, on a 2D screen you can show up to 2D. In our 3D world, only up to 3D can be expressed. But language and mathematics have no such limit, because we don't need to grasp the graph, its image, all at once. If you give up physical form, you can describe any number of dimensions. Thus, in mathematics or programming, arrays can nest endlessly, increasing dimensions while remaining very simple. By adding subscripts x, 1D, 2D, 3D, 4D, 5D, 6D, you can express dimensions. These are called coordinates. It is like 2, 6 or 7, 3 on a shogi board. My point is that humans living in 3D are not incapable of understanding 4 or more dimensions. We simply cannot perceive or depict them all at once, yet we can prove their existence and surely handle them. Is the 3D world we see truly 3-dimensional? As 3D beings, we believe we grasp 3D space at once. In fact, we lack the ability to perceive 3D simultaneously. Our retinas capture light and form images. Like camera film, a retina is 2D, so the image it captures is 2D. Therefore, we can only grasp a 2D slice of the 3D world at any instant. Whether our world is 3D is not directly perceived, but inferred with some probability. Humans see with stereo eyes, meaning 2 eyes. The brain merely infers 3-dimensionality from 2 slightly different 2-dimensional images captured from different angles. You might say, but we can touch things and move them. Even then, we do not grasp the entire surface of what we see in 3 dimensions, but infer it indirectly from first-hand information obtained by the palm, which itself has a surface. Projection. Next, let me talk about shadows, a hint for solving dimensional mysteries. A shadow is like a slice of information from a solid. It is part of the solid's information, that is, the solid with one dimension removed. The shape of the shadow changes according to the shape of the original solid. Furthermore, a shadow changes with the direction of the light and the distance from the light source. Thus, the shadow of a 3-dimensional solid is a collection of 2-dimensional shapes. By contrast, the shadow cast by a 2-dimensional plane is just a line with only length, 1 dimension. Projecting a solid shadow like this is called projection. Projection is the operation of cutting off only part of an object's information that belongs to a lower dimension. For example, measuring height projects 3 dimensions down to 1. Measuring length or area is the same. Why do we measure length or area? Because it makes understanding objects easier. It is far simpler and more accurate than grasping a complex solid all at once. To capture or reproduce shapes, we draw diagrams from various angles. It is similar. As I said earlier, our eyes capture 3 dimensions only as 2. That too is an act of projecting the solid we see. Such mathematical or geometric ways of perceiving things have raised the dimension of human intelligence. Discovery of dimensions. Euclid, the father of geometry I mentioned earlier, said the boundary of a solid is a surface, the boundary of a surface is a line, and the boundary of a line is a point, but this only goes up to 3 dimensions. The one who broke this limit was the French mathematician Henri Poincaré. He lived until 1912, so that is fairly recent. He showed the essence of geometry and creativity. Euclid named things that already existed. Poincaré, on the other hand, said of dimensions, an object whose boundary is 0-dimensional is 1-dimensional. Its ends are points. An object whose boundary is 1-dimensional is 2-dimensional. Its ends are lines. An object whose boundary is 2-dimensional is 3-dimensional. Its ends are surfaces. An object whose boundary is 3-dimensional is 4-dimensional. Its ends are solids, thus redefining how we view objects. Indeed, by this method, geometry can handle 4 dimensions and beyond. Poincaré was inspiring because he named things that do not exist or are invisible. A 4-dimensional square is called a hypercube, but we cannot see one, and drawing it is even harder. Still, we can depict something like it. This figure, called a regular 8-cell, is a drawing of a hypercube made by stacking projections of 3D cubes. Probably, the 5th dimension in the film Interstellar means 4 spatial dimensions minus time, unfolded into 3D only while the 3D protagonist is in 4D space. Unfolding a cube into a plane makes a cross-shaped 2D diagram. Likewise, unfolding a hypercube should produce a cross-shaped solid. For a 4D hypercube, its net should be a solid composed of 8 connected 3D cubes. Thus, in Interstellar, it is shown as a net of a hypercube with many identical rooms lined up. The 3D hero moves by jumping through countless 3D spaces unfolded from 4D. What would happen if a hypersolid appeared in reality? If a 3D cube appeared in a 2D world, the 2D beings could see only the cube's sliced planes. They would see shapes ranging from a point up to a hexagon. Likewise, if a 4D hypercube appeared in our 3D world, we could see only its sliced solids, appearing as shapes from a point up to an octahedron. Therefore, a 4D hypersolid in 3D would appear and disappear, change shape, and perhaps change position. If our 3D world had another extra dimension, and the 4D projection, or slice, spread before us as 3D, objects around us would have to change size, or shape, or teleport. In our world, objects do not appear from nothing, or move instantly. So where are the extra dimensions? According to recent research, it is likely that our world has 4 or more dimensions. That means extra dimensions exist in places we cannot see or grasp. What, fundamentally, is 4-dimensional space? 4-dimensional space should have far more degrees of freedom than three-dimensional space. From our 3D standpoint, let me explain how much freedom a 4D being would have. First, it could pass through walls. It could also teleport. It could mirror flip objects, or its own body left to right. It could even turn its inside surface out. Resizing itself would be easy too. These are routine tricks in 3D CG production, because 3D CG is geometry. Let's tidy up the definition of a dimension. A surface is two-dimensional. But is a curved surface still two-dimensional? Dimension means the number of necessary axes. So even on a curved surface, you can move only in two directions. Another question is time a dimension? In Einstein's special relativity, the three dimensions plus time are treated as four-dimensional. The three spatial axes plus time together are called space-time. Unlike other axes, time moves in only one direction. Because that offers no two-way freedom, I will not count it here. In general relativity, curved space appears. Einstein proposed that space containing mass is curved. He imagined that greater mass means greater curvature, which we feel as gravity. Thus, gravity is the amount of bending in that region. Adding curvature as another axis lets us regard space as four-dimensional. Geometry on non-flat surfaces, like a sphere, is called non-Euclidean geometry. Euclidean geometry drawn on flat planes matches our intuitive sense of space. Because we cannot picture bent 3D space directly, we draw 3D in 2D and use non-Euclidean rules to hint at 4D. Therefore, orbital calculations based on relativity need non-Euclidean geometry to include gravity's curvature. In addition, we think of the ground as flat in everyday life. Even in construction, long bridges must account for Earth's curvature, so non-Euclidean geometry is required. Light bending due to the sun's gravity has been observed. Capturing light that bends, though it should travel straight, shows that space itself is curved. Our world is not three-dimensional. There is a theory called superstring theory. This theory says the universe has 10 dimensions, 9 spatial plus time, and that gravity spreads into higher dimensions, explaining why gravity is overwhelmingly weaker than the weak force, strong force, and electromagnetism. Gravity is only 1 part in 10 to the 42nd power. That is, 1 followed by 42 zeros of the strength of electromagnetism. So it is said to be difficult to describe the 4 forces within a single theory. Superstring theory is unproven experimentally, but the idea of higher dimensional space has influenced much research. So, what is higher dimensional space, like in superstring theory? Superstring theory introduces the idea that higher dimensional space is compactified and hidden. This is called compactification of dimensions. But why does the theory need 9 spatial dimensions? According to superstring theory, every known particle, photons, gluons, quarks, neutrinos, and the rest, is thought to be an extremely tiny string, roughly 10 to the minus 34 meters long, and different vibration patterns of that string are observed as different particles. Matching the particles already found to string vibrations needs more than 3 dimensions, so they expanded it to 9. If string vibrations span many dimensions, it seems similar to computer graphics. A single pixel can store 3 color axes and even depth. With an alpha channel, each pixel can hold various additional factors. If the universe is 4-dimensional or higher, how can we verify the number of spatial dimensions? In fact, there is a rule for confirming the dimension count. It is Newton's law of universal gravitation. The force between 2 masses is proportional to their masses and inversely proportional to the square of their separation. If the distance doubles, gravity becomes 1/4. If the distance triples, gravity becomes 1/9. This inverse square law also holds for light, that is, electromagnetic waves. In 3-dimensional space, any force radiating uniformly weakens with distance squared. In a 2-dimensional world, it weakens in direct proportion to distance. In 3 dimensions, the influence spreads across the surface of a sphere, 2 dimensions, so the effect falls off with distance squared. Thus, in higher dimensional space, gravity would rise sharply as distance shrinks. Watching how distance and gravity change lets us detect whether the space is four-dimensional or more. But how can we measure gravity on such a microscopic scale? That is where CERN comes in. Yes, the Large Hadron Collider at CERN. An accelerator speeds particles such as protons to near light speed and smashes them together. In its 27-kilometer vacuum ring, particles collide at about 300,000 kilometers per second, and the collision energy turns into matter, creating particles that did not exist before. The collision energy is converted into new particles. If the collision energy pushes extra dimensions beyond quantum size, phenomena impossible in 3D space should occur. If gravity produced in this experiment does not follow the inverse square law, it will be evidence that higher dimensional space exists in the quantum realm. The experiment also suggests that the resulting supergravity could create micro-black holes. If Earth were compressed to a 1 centimeter ball, it would become a black hole. Black holes are thought to form when matter is squeezed to the extreme. If extra dimensions exist, gravity at close range could become 10 to the 40th times stronger, so black holes might even form inside the accelerator. A black hole appearing on Earth sounds frightening. However, theory says such a black hole would evaporate in 10 to the minus 26 seconds. Can we use higher dimensional space? Doraemon's four-dimensional pocket might be one use. I would like to teleport. If size is free, becoming Ultraman is another option. CERN's experiment suggests that if space of 4 or more dimensions exists, we can probably confirm it. But using that space is another matter. So far, 4+ dimensional space seems extremely small at quantum scale, so humans cannot use it directly. Even so, discovering higher dimensions would surely have huge impact on theoretical physics and technology. Many mysteries of quantum theory might be solved, and quantum computers, faster than light entanglement communication, and room temperature superconductivity could advance dramatically. Perhaps we could create materials stronger than carbon nanotubes, unbreakable substances, or harvest unlimited energy from micro-black holes. This is only speculation, but the uncertainty principle, why a quantum's speed and position cannot be fixed simultaneously, and the reason a quantum's position exists as a probability due to superposition and even distance-independent interactions like quantum entanglement, make perfect sense if extra dimensions, that is, 4 or more, exist at quantum scale. As I said at the start, a 4-dimensional hypersolid in a 3-dimensional world appears and disappears, changes shape, and may change position. The behavior of quanta in quantum theory closely resembles how a 4-dimensional object would behave when it appears in 3D, which is striking. Among quantum behaviors, one most strongly suggests extra dimensions. That is the quantum tunneling effect. In brief, because a quantum's position is probabilistic, at extremely small scales, it can pass through an object if it is very close. This seems less like the quantum moving through the object, and more like instant movement enabled by extra dimensions. Holographic principle overturns our dimensional common sense. We have never questioned that space is 3-dimensional. As said, in 3D, the strength of gravity and light weakens with the square of distance, while in 2D, it weakens in direct proportion to distance. If the dimension of space differed, physics itself would change, and the results of everyday phenomena would change too. The holographic principle states that events in two worlds with different dimensions, such as 2D and 3D, can be regarded as the same, or equivalent. In short, 2D, 3D, and 4D all contain the same amount of information. A hologram is a device that projects what seems to be a real 3D object on a plane. Though flat, changing the angle lets you see the object from another direction. The holographic principle is not identical, but like a hologram, it reproduces a higher dimension from a lower one. That is, it recreates the higher from the lower, which is very similar. So, what exactly is the holographic principle? In this principle, among the 4 fundamental forces of nature, the weak, strong, electromagnetic, and gravitational, gravity, which is the hardest to unify, is regarded as an illusory force. This is possible in virtual space, that is, in geometry or computers, but some think the principle might apply to our real world too. Quantum theory already covers areas understood only geometrically. Perhaps it is an event in another dimension, with laws but without proof. The holographic principle was born from mysteries of black holes. All matter possesses information, entropy, such as its position and velocity. Entropy is known to increase in amount, that is, complexity, over time. Yet the information of matter swallowed by a black hole seems unobservable from outside and appears lost. A black hole is a massive body compressed to a point by its immense gravity, from which even light cannot escape. In the 1970s, it was found that the area of a black hole's surface, the event horizon, never decreases. Thus, a black hole was thought to enlarge its surface area according to the mass it consumed. This phenomenon was found to resemble, in equations, the second law of thermodynamics, which says entropy never decreases. They then concluded that a black hole's surface area is proportional to the information, or entropy, inside it. In other words, matter swallowed by a black hole is not lost, but remains on the event horizon. However, this theory also produces a contradiction. In 3D, saving more data on, say, a USB drive means increasing the drive's volume. Generally, the amount of information is proportional to volume, not area. In the 1990s, Dutch physicist Gerardus 't Hooft and American physicist Leonard Susskind proposed an idea. Information that existed in 3D is written onto the black hole's 2D surface, the event horizon, when it is swallowed. In other words, the black hole's surface acts like hologram film that stores all information swallowed. This idea was extended to suggest that any space, not just black holes, stores its information on its 2D boundary. It is a very enticing theory because it seems plausible. Even if a hologram can show 3D from 2D, the idea that the real world works the same way feels a bit far-fetched. Yet the holographic principle began to be applied to concrete physics calculations. In 1998, Juan Maldacena at Princeton University announced that results in ADES space and in conformal field theory, CFT, match. This is the conjecture that a gravity theory in ADES space is equivalent to a CFT in one fewer dimension. Such a relationship is called the ADES-CFT correspondence. Equivalence means the two theories yield identical calculations. Thus, a phenomenon in 3D can be replaced by a phenomenon in 2D. Using ADES-CFT lets a complex quantum mechanical calculation be replaced by a gravity theory calculation in one higher dimension, making it far easier. It is like a converter between dimensions. Applications have already been found, suggesting space-time, like matter from atoms, might be made of unseen fundamental elements. This could overturn much of theoretical physics. In a normal hologram, a 2D plate precedes the 3D image, but here the 2D code and the 3D hyperimage are equivalent, essentially the same. Perhaps there is only one world, yet we can view it as 2D, 3D, or 4D. This seems related to the many worlds interpretation of quantum mechanics. Many worlds interprets quantum superposition, holding all possibilities simultaneously, as each quantum overlapping many worlds. People often confuse it with parallel worlds, but it differs greatly. Parallel worlds suggest whole copies of this world exist, whereas many worlds happens only in the invisible, ultra-small quantum realm. Thus, countless quanta each have their own similar world. At that tiny scale, quanta effectively possess more than 3 spatial dimensions. Humanity is now challenging the discovery of macroscopic extra dimensions, ones directly related to us, in holographic cosmology. We have seen that geometry itself expresses how the world works, and by viewing natural phenomena from more than 3 dimensions, it becomes a powerful tool to clarify the hard to understand. We know geometry greatly aids architecture and industry, but we rarely feel its power directly. Through geometry today, I feel I have glimpsed what it means to perceive objects. Humanity will continue to discover new dimensions through the power of geometry.